Hello guys, so today we are going to jump into kind of the second half of our unit, which is electrochemistry. And so that's kind of the second half. It's what we'll cover for the next 3 class periods. And we're going to start by going over a redox review or an oxidation reduction review. Now guys, this is a review from Unit 4, and there is a whole video on redox posted to the Coyote Chemist YouTube over redox reaction. So I'm going to go pretty quickly through this since it is a since this should be a review. So redox reaction is, again, it's anytime we're transferring one or more electron. And you have to have oxidation to have reduction. They have to go hand in hand. So oxidation cannot occur without reduction. So oxidation is when we have a loss of electrons or an increase in our oxidation number. So our charge would go up in oxidation. Reduction, we have a gain of electrons and we have a decrease in our oxidation numbers. Remember, electrons are negative, so when we gain electrons, our charge is going to go down. We told you guys 2 ways to remember which one is which. So oil rig stands for oxidation is loss, reduction is gain. Or Leo the lion says GR, lose electrons equals oxidation, gain electrons equals reduction. So those are just ways to remember that oxidation, you lose electrons, reduction, you gain electrons. Then we briefly talked about an oxidizing and reducing agent. Those are no longer covered on the AP exam, but basically the oxidizing agent is the substance which is reduced, and then so it causes someone else to be oxidized. Reducing agent is oxidized and causes something else to be reduced. But again, those aren't covered on the AP exam, so not super important that you know them. Just be familiar with the terms. All right, and then if you remember, we use the half reaction method to balance redox equations. This is really going to be something we're going to use a lot more, is those half reactions. Today, or this unit is going to be using those half reactions. So these are just reactions that show either the loss or gain of electrons. It shows us the number of electrons transferred. So like right here, we have Fe positive 2. Turns into Fe3 plus an electron. So because our charge has gone up, we know that we've lost an electron there. And then in our second half reaction, we have copper positive 2 plus 2 electrons yields copper. Again, our charge has gone down, so we've gained electrons because electrons are negative. Okay. To be able to figure out what's happening to our charge, we do need to figure out our oxidation state or our oxidation numbers. So kind of some brief things. Elements always have an oxidation state of 0. If you do have a charge, then the oxidation number is going to be the charge. Oxygen is always -2 in covalent compounds. Hydrogen is +1 in covalent compounds. Fluorine should be -1. Your oxidation state should always add up to 0, or the charge of the ion. All right, so I'm just going to go through a couple of these and then have you guys do a couple on your own. So I'll start with ClO2, or Cl2O, my bad. Cl2, oh my goodness. Let's see if I can zoom in. There we go. Worked that time. Okay, so we have chlorine and oxygen. So we know from up here that oxygen is always -2. Oh, that's not what I wanted. -2. All right. To balance out our charge, our total charge of our compound, we don't have a charge here, so it needs to add up to 0. So I have 2 chlorines that we need a total charge of +2 to balance that out. So each chlorine would then have a +1 charge. Okay, so then our next one is PBr3. The most electronegative element is always going to take on its normal charge. So in that case, bromine is much more electronegative than phosphorus is. So bromine is going to take on its normal charge of -1. And since we have 3 bromines, each with a -1 charge, that means our phosphorus is going to take on a +3 oxidation number. Okay, I'll do one more with you guys, and then I'm going to leave you the last 2 to do on your own. So in this one, we have HPO3 -2. So that means the total charge of our oxidation of our oxidation numbers needs to add up to -2. So we know oxygen is always -2. We know hydrogen would be +1. So I have 3 oxygens, each with a -2 charge, gives me a total of -6 plus 1. So what does it need to be to add up to -2? My phosphorus would have to be +5 then to add up to -2. Okay, so you guys go ahead and do the last two, pause the video, figure out their oxidation numbers, and then come back. Okay, so for the last two, I got that manganese would be a +7, oxygen would be a -2, and then nitrogen would be -3, and hydrogen would be +1. Okay, I know that was a really quick review, but we did learn this already this year. So again, if you're like, what the heck just happened? Maybe go watch that video from Unit 4 just to kind of check yourself out. Okay. So now we're going to talk about balancing redox reactions by the half reaction method. And I will say most of the redox reactions we're going to do in this unit are pretty easy and pretty self-explanatory with how we're going to, or not self-explanatory, but pretty easy basic redox reactions. So first thing you're going to do is you're going to write the half reactions. Balance everything except for oxygen and hydrogen. We balance oxygen by adding water, and we balance hydrogen by adding H+. If you have one that says it occurs in basic, then we add hydroxide ions to both sides, form water if you can, and then cancel out any waters that are on both sides of the equation. Then we balance our charge by adding electrons to the more positive side. We're going to make number of electrons lost equal to number of electrons gained by multiplying each half reaction by a factor. Then we'll add the half reactions together, cancel out anything that's the same on both sides, and check to see that everything is balanced. Okay, so we're going to start with this first one. And this first one is a really good example of what we would be working with this year during this unit, I guess I should say. So we have Al plus Cu +2 yields Al +3 plus Cu. And this happens in an acidic solution. Okay, so first thing we need to do is pull out our half reactions. What we're looking for is basically how did our charge change. So my first half reaction that I see is that we have aluminum. Solid aluminum is going to yield aluminum ions. And then the second half reaction that we have is that our copper ions are going to react and form solid copper. Okay, so that's step one, is just to write our half reactions. Step two, balance all other elements other than hydrogen and oxygen. Well, these are already balanced because we have one aluminum on both sides and one copper, and we don't have any oxygen or hydrogen. So we don't need to balance our oxygen or balance our hydrogen. And again, it occurs in acidic solution, so we don't need to add hydroxide. Next, what we're going to do is we are going to balance our charge by adding electrons to the more positive side. So over in our top reaction, we have aluminum +3 on our right. So that aluminum +3 has lost 3 electrons there to become that aluminum +3. And then our copper +2 is the more positive one on that side. So it has gained 2 electrons to become copper. Okay, so that is that step of just adding electrons to that side. Now what we need to do is we need to make our electrons lost equal to our electrons gained. And we're going to do that by multiplying by a factor. So we have 2 and 3, so our common multiple would be 6. So I'm going to multiply my top equation by 2 to get it up to 6. And I'm going to multiply my bottom equation by 3. And I'm just going to go ahead and also add these together at the same time that I'm doing that. So when I do that, I get 2 aluminum plus 6 electrons plus 3 copper 2 ions yields 2 aluminum ions plus 6 electrons plus 3 copper solids, plus 3 coppers. Cancel out things that are on both sides, so the only thing that would be canceled out here is those 6 electrons, and then we'd be left with our final redox reaction of 2 aluminum. I'll write it out over here. So 2 aluminum plus 3 copper ions yields, I'll write it out of space, 2 aluminum ions plus 3 solid copper. And that would be our final balanced redox reaction. This one's going to be very similar to a lot of the reactions we're working with this unit. So if you understood how to do that, you should be in good shape. Now I want you guys to pause the video and try to work this one out on your own. Okay, so when I did it, I got 8H plus 5 iron positive 2 ions plus MnO4 negative 1 yields 5 Fe positive 3 plus Mn positive 2 plus 4H2O. Okay, so really where we're going to be doing this is these redox reactions tie directly into electrochemistry, because we can use a redox reaction to drive an electrochemical reaction and create electricity, essentially, so we can use that. So it is going to be important that you do understand redox reactions for this unit. We really have 2 ways that we will see this done. We will see using that chemical energy into electrical energy. That is in a galvanic cell and an electrolytic cell. So in a galvanic cell, chemical energy is changed into electrical energy. It can also be called in a voltaic cell, and this is a spontaneous reaction or thermodynamically favorable reaction. An electrolytic cell, same thing, different. Electrical energy is changed into chemical energy, and this happens in a non-spontaneous reaction. Okay, I'm going to talk a little bit about electrolytic cells, just kind of hit very, very key, like a few key things about them, but really we're going to talk about this more next week when we talk about Faraday's law. It just makes more sense to talk about them then. So the chemical reaction that we want to happen is non-spontaneous. We can basically make our reaction happen by the addition of electrons from an outside source. This results in the conversion of electrical energy into chemical energy. We see this in the electrolysis of water or salt solution or silver plating. Kind of the big key thing about electrolytic cells versus galvanic cells is electrolytic cells have to have a power source and galvanic cells do not. So galvanic cells happen on their own and they make electrical energy, whereas electrolytic cells, you have to have some sort of power source to make the reaction take place. So that's, again, just very basic. We will talk more about electrolytic cells next week. But today, what we're really going to focus on is galvanic cells. So in a galvanic cell, and another word for a galvanic cell is just a battery. So this is what's happening in your batteries. But in a galvanic cells, the transfer of electrons can actually be used as an energy source if it's harnessed. What we're going to do is we're going to separate the 2 half reactions and require our electron transfer to occur through a wire. So then our electron flow, which remember, electricity is just flow of electrons, can be used to do other useful work. The solutions must also be connected not just through the wire, but in another way, or else the charge is going to become really unbalanced and the electrical flow will stop. This is often used by a salt bridge. Salt bridge is any kind of porous medium that is soaked in a salt solution, essentially. And basically ions flow from one compartment to another to keep the net charge 0. Okay, so I am going to now spend some time talking through a galvanic cell. All right, and I'll just tell you guys, I have a lot of notes here about my galvanic cells, so I'm going to go through them and talk through them. So first thing that we want to see is we want to see those two half reactions. So you can see that we have zinc over here on the left side of our thing, and we have copper over here. All right, so what's happening, we can see that zinc is giving up those electrons. And we can see that because we can see that the electrons are flowing from the zinc. So zinc is giving up electrons, or zinc is being oxidized. All right, and then copper is taking in those electrons. So zinc is giving up those electrons, copper is taking in those electrons. And you may be sitting here thinking, Miss Treese, you said no power source, but what is this? Guys, this is not a power source, but this is just something that we would use to measure the voltage. It's purely telling me basically how many electrons are flowing through the wire. So 1.1 is what we see there. All right. Okay, so you can see zinc is giving up those electrons are flowing through into the copper solution. So zinc is being oxidized, copper is being reduced. All right, now if this continued, if we kind of just started this, what would happen is this reaction would start, but it would stop almost immediately because we would have a really big buildup of negative charge over on the side of our copper where it's gaining all of those electrons, and we would have a really big charge of positive over where zinc is giving up those electrons. And so we would get stuck essentially. And that's where the salt bridge comes in. So if we don't have the salt bridge, our reaction is not going to keep happening because we're going to get a big buildup charge and it's not going to be able to continue. So basically what your salt bridge needs to be is it needs to be a porous material that allows spectator ions, and those are ions that aren't even participating in the reaction at all whatsoever, to flow through it. All right, so in this case we have NaCl. And basically our Na is going to, or our positive ions, our cation, is going to move towards the cathode. And the cathode is where our reduction is taking place. So it's going to move towards the negative, the buildup of negative charge. And our anions are going to move towards the anode, or where oxidation is taking place, where we have that big buildup of positive charge. All right, so cations are moving towards the cathode, anions will move towards the anode, and it's just there to balance out those charges that we're getting in making, like, in reduction and oxidation. I don't know why I couldn't say those words. Okay, so that's kind of the basics of how it's working. Your oxidation is occurring at the anode, and electrons travel through the wire to the cathode where reduction takes place. And we have that salt bridge there to balance out our charges. All right. Now then, the next thing I want to talk about is kind of looking at these close-up pictures of what's actually going on. So in our zinc, what's going on in our half reaction is that our solid zinc is being converted into aqueous zinc ions. So over time, what's actually happening is my zinc bar here, it was actually going to lose mass. And it's being converted into that solution because it's being converted into those zinc ions. All right, so it's losing mass. And you can kind of see, here's a picture of the anode and the cathode after reacting for a while. You can see that our zinc anode has reacted quite a bit, and that a lot of the zinc is gone then. So then on the other side are copper ions. So copper ions in our solution are being converted into solid copper, and they are actually going to then gain mass. So we're going to gain mass over here. Yeah, so then again, you can see on that cathode right there that it's obviously gotten bigger from the top, and so it's gaining that mass there. Okay, that's kind of the very basics of how these things work. So a few key points is our anode. So our anode is always the electrode at which oxidation occurs. Again, the anode is going to lose mass because it is turning from solid into that aqueous solution there. Cathode is where reduction occurs. And after a period of time, it will be larger because the ions in solution are forming solid copper on your cathode. All right, this is just kind of a helpful reminder here. So an ox and a red cat, oxidation occurs at the anode, reduction occurs at the cathode. And then fat cat is electrons travel from anode to cathode in a galvanic cell. Another way I always remembered it, that I liked it, is that it's alphabetical. So it flows from A to C. Okay, this video is very annoying, but it is so helpful to help you guys remember how a galvanic cell is going to flow and work. So I'm saying it's required viewing. You need to log off this video and you need to go and watch this because it's really going to help you remember what's happening in a galvanic cell. And so you need to watch the whole video, maybe even watch it twice, and you will be really annoyed with me. You'll be like, Miss Treese, that was the worst video I've ever seen in my life. Worst song ever. But you will remember because it's so catchy and he says the same things a million times. So it's worth it. I promise. So yeah, start at the anode. The other thing I want to talk about is that today we are assigning something called the skill builder. Now with the skill builder, this is something that won't be due until the day of your test. And we don't expect you guys to know all of the answers to it today because we've only covered galvanic cells. So that's all you really are going to be able to answer on the skill builder up to this point. But it's just a really great learning tool for you guys that I think you'll really benefit from doing. So if you start working on it and you're like, okay, I'm to the point now where I don't know anything, that's fine. Stop working on it and come back another day. All right. Have a great day. Bye, guys.